Alright, in this video we're going to look at exact ordinary differential equations. Now, before we go into these, an idea that is going to be useful and actually fundamental in discussing exact ODEs is the idea of a total differential. So let's define a total differential. So given a continuous function of two variables, x and y, continuous function f of xy, okay, we define the total differential, differential is defined as follows. Let's say is defined as so total differential of f is df is given by partial f partial x dx plus partial f partial y dy in terms of the subscript notation is fx dx plus fy dy. So this is your total differential of a function f of xy. Let's look at an example. So if f is equal to x squared y minus y squared over x, let's say, and then plus 2x, okay. So what this definition is saying is that the total differential is simply going to be the partial derivative of f with respect to x, and then that we multiply by dx. So here the partial derivative of this with respect to x, we've got x here, x there. Remember, when you do partial differentiation, you just assume that x only is the variable, everything else is constant. So here we're going to have dx, 2xy. Here derivative of 1 over x is negative 1 over x squared, so that term is going to become plus, and then derivative of 2x is 2. So the first term is going to be 2xy plus y squared over x squared plus 2 times dx. And then for the second term, we are now going to be differentiating this thing with respect to y. There's y here and there's y here. There's no y here. So derivative of this with respect to y is 0. Derivative of this one, derivative of y is 1. So that's just going to be x squared. Derivative of y squared there is 2y. Okay, so that is going to be the total differential of this function f here. Now, so we're going to relate this to ODEs. Okay, so it so happens that some ODEs are actually such that they are the total differential of some function f. So some ODEs are such that remember, so we write our ODEs in this form. So some ODEs are such that this left hand side here is just a total differential of some function f. Okay, so maybe let's just write out the notes here. So some ODEs are such that this thing happens to correspond to the total differential total differential of some function f which we don't know. And so if we can find this function here, then we have solved this differential equation. What do we mean by this corresponds to some total differential? Well, basically we mean that this left hand side here corresponds to df, okay, which is the total differential. Okay, or alternatively, let's write it like this. So what we are saying is that m dx plus n dy is actually equal to fx dx plus fy dy. Okay, so we're basically saying that this differential here corresponds to the total differential of the function f of xy. Okay, when this happens, then the ODE is called an exact ODE. Okay, so when this happens here, so let's say such ODEs are called exact ODEs. Exact ODEs. Okay, what this equation, let's call it asterisk, what this equation is implying, so from that equation there, what it is implying is that, so the coefficient of dx this side must be the same as the coefficient of dx there, and the coefficient of dy must be the same as the coefficient of dy there. So this must be equal to that, and that must be equal to that. So what that equation is implying is that m is equal to fx, and n is equal to fy. Okay, so remember, m is known, n is known, f is the unknown. Okay, now from these two here, if we differentiate this one with respect to y, okay, so let's remove this here. We differentiate that with respect to y, then we're going to get my is equals to fyx. Differentiate this one with respect to x, then we're going to get nx is equal to fxy. Now this is a cross derivative here. Now since f is a continuous function, okay, then we know that for continuous functions the cross derivative is going to be equal. So if you differentiate f with respect to x first, then y, you're going to get the same thing. We differentiate it with respect to y first, then x. Okay, so what this is implying is that these two must be equal as well. Okay, so we have my must be equal to nx. This is actually the criteria that we use to test if an ODE is exact or not. So if my is equals to nx, then we say the ODE is exact. So let's put a definition here. So based on this, we are going to write the ODE m dx plus n dy equal to 0. So this ODE is called exact, or is said to be exact if my is equal to nx. We have already shown how that comes about. All right, so what's happening here is that here this side is just df. Now so the assignment in solving that ODE is going to be to go from this stage back to that stage here. Now we've already seen that going this way involves partial differentiation. Okay, so we should expect that going the other way around is going to involve integration. Okay, so if we find that an ODE is an exact ODE, then we must find f. We're going to have to start from this, find f by integration, and then we have got the solution of the ODE. Right, so let's look at some examples. Okay, all right, so we've got 3 examples here. This first example, you might actually recognize it from the previous discussion, because it's exactly this total differential here. Okay, so we already know the answer is that, but we're going to take you through the process of how to go from this back to that. All right, and then the second one has got an initial condition here, so we're going to find the general solution of this, then apply the initial condition, and then this last one again, we're just going to find the general solution. So first of all, we're going to solve these two, then we're going to give you a chance to have a go at this one before you can scroll down to our solution. Now again, here we are going to go through these, assuming that we did not know that the equation, the given ODE is exact. So this is going to help you when you attempt problems that are not classified according to sections of types of ODEs, because in your assessment you might just be given an ODE without you being told whether it's separable, whether it's exact or homogeneous. Those are the ones we have covered so far in these videos. All right, so to start with, could this ODE be separable? And the quick answer is no, because for separation of variables, we need to factorize, be able to factorize these, like the x's alone and then the y's alone. Just look at this one with only two terms. You can see that there's no way you can factor out y here or the x's to be on their own. So straight away we can see that this ODE is not going to be separable. Okay, is it homogeneous? Then again, for an ODE to be homogeneous, this term must be homogeneous and that one must be homogeneous. We said for terms involving powers of x, like polynomials, then the powers of x must add up to the same thing in each term. If you look at this term, for instance, there's 1 and 1 here, so they add up to 2. But for this one, they add up to 0 and 0 here. So clearly, this equation is not going to be homogeneous as well. So not homogeneous. Okay. Then the next thing is we're going to check if it's exact. For exact, we need to use the criteria, whether we need to test whether my is equal to nx. So that is our m there. So my means we have to differentiate this thing with respect to y. I've got y here and y there. So the first term is going to give us 2x. The second term is going to give us 2y over x squared. This term is going to give us 0. Then we differentiate n with respect to x. Derivative of x squared is going to be 2x. Derivative of 1 over x is negative 1 over x squared. So that term is going to be 2y over x squared. Now you're going to notice that these two are the same. So my is equals to nx, or let's write this. So let's say ODE is exact because my is equal to nx. Okay, so if it's exact, it means that ODE is df equal to 0 of some function, which we have to find. So it means we have got fx dx plus fy dy equal to 0. So that means this coefficient here is equals to fx, and that coefficient there is equal to fy. So we're going to have two equations. So fx, I'm going to write this using this notation. So that one is equal to 2xy plus y squared over x squared plus 2. And then the other one is equal to x squared minus 2y over x. Okay, so remember, this is just m and this is n. Now, so how can we find f from here? Well, we're going to find f by integrating partially. So if we take 1, okay, and take dx partial x to the other side, then we've got partial f is equals to 2xy plus y squared over x squared plus 2 partial x. Then we can find f from here by integrating partially with respect to y. Okay, so this is the opposite of differentiating partially. So in this case, again, we assume that everything else is a constant. X is just the derivative. So our f is going to be given here. Integral of 2x is going to be x squared. And integral of 1 over x squared is going to be minus 1 over x. Integral of 2 is going to be 2x. Okay. Now, since we're integrating partially with respect to x, so this is going to have to be plus. Now, remember, if we're integrating like total integrals, you always get a constant of integration. For partial integrals, you get a function. So if you are integrating with respect to x, then you're going to get an arbitrary function of y. This is such that when we differentiate this partially with respect to x, we are going to have to get that one back, okay? Because this is going to give us, this one's going to give us 2xy. This one's going to give us y squared over x squared. This is going to give us 2. This derivative with respect to x partial is going to be 0. Right, so that's that. Now, what we are going to do is then we're going to differentiate this now partially with respect to y. So if you do that, partial f partial y is going to be x squared minus 2y over x. This term vanishes. This one becomes phi prime because we are doing derivative with respect to y. Then all we need to do is to compare this with this one, okay? So compare. We compare them, we're going to find that this term is exactly the same as that one, is exactly the same as that one, which implies that phi prime must be equal to 0. And then from there, we can say that phi is just going to be a constant. We now have f then, because we can take this and plug it back there. So therefore, f of xy is x squared y minus y squared over x plus 2x plus k. Okay, so that is that function that we're looking for. Remember, we're integrating df here. So when you integrate df, when you integrate this side, you're going to get f. Integrate this side, you're going to get k. So that means actually the solution, we can leave it like this, or we can write it as follows. So x squared y minus y squared over x plus 2x plus k equal to 0. So that is the solution of the ODE. Okay. All right, so that's the first one. We are now going to go to the second one. So in the second one there, so we have got y cosine x plus 1 over y dx. Then we have got sine x minus x over y squared plus 1 over y dy equal to 0. Then when x is pi on 6, y is equal to 1/2. So first we just have to integrate that. So again, if you try to factorize here, you are not going to be able to. So that tells us that this cannot be separable. If you try to look at the powers of x and y, you're going to find that this is not homogeneous. So then we try to work out my. My is going to be cos x minus 1 over y squared. Nx is going to be cosine x minus 1 over y squared again. So ODE is exact because nx is equals to my. So it means derivative of f with respect to x is y cosine x plus 1 over y as done before. Derivative of f with respect to y is sine x minus x over y squared plus 1 over y. All right, then to find f, we integrate this with respect to x partially, then differentiate it to compare with this one. This time I'm going to do it the other way around. I'm going to integrate this one with respect to y partially. Okay, so let's call this 2. Let's call this 1. So from 2, f is going to be, if we integrate this partially with respect to y, the first term is going to be y sine x. The second term is going to be plus x over y, because integral of minus 1 over y squared is 1 over y. Then this one is going to be ln of magnitude of y. Since we're integrating partially, this time this is going to be plus some function of x. Then we differentiate this now with respect to x, okay, which we're going to compare with this one. So derivative of the first term with respect to x is going to be y cosine x plus 1 over y plus phi prime. Okay, then if we compare with 1, comparing with 1, so you can see that this term is exactly the same as this one. This one is exactly the same as that. So that tells us that phi prime of x is going to be 0. So phi is going to be a constant. So again, it means our solution is just going to be this thing equal to 0. Y sine x plus x over y plus ln y plus a constant is equal to 0. I'm actually just going to do the same thing now, starting by integrating 1. Okay, just in case somebody is not happy with this approach. So if we integrate this with respect to x, okay, integral of cosine x is sine x. So we're going to find f is y sine x. Then integral of 1 over y with respect to x is going to be x over y. Then we are going to say this plus some function of y. Then if we differentiate this with respect to y, this is going to be sine x minus x over y squared plus lambda prime of y. Then we've got to compare this with 2. Okay, so comparing with 2 gives, so we've got sine x here, and in 2 got sine x. We have got yeah, let me just write the equation 2 just below this one here. So in 2 we've got fy equal sine x minus x over y squared plus 1 over y. Okay, so that's 2 there. So if you compare here, you can see that these two correspond, so we must have lambda prime must be equal to 1 over y. Then if we integrate this, it tells us that lambda is ln of magnitude of y plus a constant. Then we can take this and plug it back there, and it's going to give us exactly the same answer. Let me just write it again. So so we've got y sine x plus x over y plus ln y plus k equal to 0. Then remember, this time we have got an initial condition. So when x is pi over 6, y is half. So we're going to plug in x is pi over 6 there, and y is 1/2. So so substituting that, it's going to give us y over half sine pi over 6 here. X is pi over 6 divided by 1/2 there. Then ln 1/2 plus k is equal to 0. Okay. So the first term, sine pi over 6 is just 1/2, so it's going to be 1 over 4. So it's going to be pi over 3 ln 1/2 plus k equal to 0. So this is telling us that k is going to be equal to ln 2 minus 1 over 4 minus pi over 3. Then the particular solution, if you plug in this k here, no, not there, here, okay, so we're going to get y sine x plus x over y plus ln y, okay, then plus ln 2 minus 1 over 4 pi over 3 equal to 0. If you collect terms here, this is going to be ln 2y minus 1 over 4 minus pi over 3 equal to 0. Right, so that brings us to the end of that one. What we're going to do now is we're going to give you a chance to have a go at the third one. So if you just want to pause the video and then have a go at this part C. So part C, you just want to find general solution there is no initial condition. Okay, and then when you press play, then you can compare your answer to our answer. Okay, all right, so we're hoping that you have now had an attempt on C. Now going to scroll down to show you our solution. If you haven't, please just pause the video and work through the problem first. You'll benefit more that way. All right. Okay, so in C, so first of all, if we try to see whether this is factorable, we're going to find that you can't factorize that. And well, you can't factorize that either. It's a power of 4 there. So that's definitely not separable. And then these are polynomials, but you can see here powers add up to 2, here powers add up to 3. So definitely not homogeneous. So the next thing we do is try to see whether it's exact. If we differentiate this with respect to y, we got 4xy plus 4. Differentiate this one with respect to x, we get 4xy plus 4. So it definitely is exact. So that means there is some function f which is such that this thing is a total differential of. So, and the derivative of f with respect to x will be given by m. The derivative of f with respect to y given by n. And then from this, so from 1, we can integrate this with respect to x partially. So this term of integrate with respect to x is going to be x cubed. That one is going to be x squared, y squared, integral of 2x. And the last one is going to be 4xy. Then this is going to be plus some function of y, because f is a function of x and y. Then we're going to differentiate this partially with respect to y and compare with 2. So derivative of this one is going to be 0. Derivative of this one is going to be 2x squared y. Derivative of this one is going to be 4x. Derivative of this one is 5 prime. So if we compare, the first term corresponds, second term corresponds, so this one must be equal to 5. So let's say comparing gives, so 5 prime must be equal to 5y to the power of 4, which tells us that phi is y to the power of 5 if we integrate the thing plus a constant. Then we take this and plug it back there, equate it to 0, and that's our solution. So therefore x cubed plus x squared y squared, 4xy plus y to the power 5 plus k equals to 0 is the solution. All right, so it brings us to the end of this video. Thanks for watching this. If you're finding these videos helpful, please, you can subscribe so that you get notified whenever we post new material. Thank you.